So far, we've studied the basics of digital logic as well as design for combinational and sequential circuits. Now we'll look at complementary metal oxide semiconductor technology. In the companion presentation, we'll also look at basic programmable logic devices such as read-only memories, programmable logic arrays, programmable array logic, field programmable gate array devices. We'll need to define the design space. The design space describes the target technologies and the parameters used to characterize them. Digital circuits are constructed with integrated circuits. An integrated circuit, abbreviated IC, is a silicon semiconductor crystal, informally called a chip, containing the electronic components for the digital gates and storage elements. As integrated circuit technology has improved, there have been increases in the number of gates present in a single silicon chip. We use the term small, medium, large, and very large-scale integrated device to differentiate between these levels. Small-scale integrated circuit (SSI) devices contain several independent primitive gates in a single package. The inputs and outputs of the gates are connected directly to the pins in the package. The number of gates is usually less than 10 and is limited by the number of pins available on the integrated circuit. Medium-scale integrated devices have approximately 10 to 100 gates in a single package. They usually perform specific elementary digital functions, such as the addition of 4 bits. MSI digital functions are similar to functional blocks that we talked about in Chapter 3. Large-scale integrated devices, LSI devices, contain between 100 and a few thousand gates in a single package. They include digital systems such as small processors, small memories, and programmable modules. Very large-scale integrated devices contain several thousands to hundreds of millions of gates in a single package. Examples are complex microprocessor and digital signal processing chips. Because of their small transistor dimensions, high density, and comparatively low cost, VLSI devices have revolutionized digital system and computer design. VLSI technology enables designers to create complex structures that previously were not economical to manufacture. Currently, silicon-based complementary metal oxide semiconductor (CMOS) technology dominates due to its high circuit density, high performance, and low power consumptions. There are some different implementation technologies, and they're discussed in the text if you're interested in looking at them. The foundation for CMOS technology is the metal oxide semiconductor transistor. Transistors and the interconnections between them are fabricated as elements of an integrated circuit die, less formally referred to as a chip. Each rectangular die is cut from a very thin slice of crystalline silicon called a wafer. In the most modern fabrication facilities for making integrated circuits, wafers are typically about a foot in diameter. Here we see a sketch of a transistor. For a sense of scale, we're looking at 1/1000th of a human hair. The substrate is the basic wafer material. The fabrication process modifies the substrate to be highly conductive in the source and drain regions. The conductive polysilicon gate has been deposited on top of a very thin insulating layer of silicon dioxide. The resulting structure consists of 2 identical conductive regions, the source and the drain, with a gap in between that lies under the gate. This is referred to as the channel. In the normal operation of an N-channel MOS transistor, the drain is by definition at a higher voltage than the source. When the gate voltage is at least the threshold voltage of the transistor above the source voltage, and the drain voltage is sufficiently above the source voltage, a thin layer of the substrate just below the thin gate insulation becomes a conducting layer between the source and the drain. This permits a current to flow between the source and the drain. In this case, the transistor is said to be on. On the other hand, if the gate-to-source voltage is less than the threshold voltage, the channel will be absent, lacking significant current flow. Under this condition, the transistor is said to be off. Because of the on-off dichotomy, a switch-like behavior is a good first-order model for an MOS transistor. The behavior of the MOS transistor model depends on the transistor type. CMOS technology employs 2 types of transistors, N-channel and P-channel. The 2 transistor types differ in characteristics of the semiconductor material used in their implementation and the mechanism governing the conduction of a current through them. The behavior we just described a couple of slides ago fits the N-channel model. The transistor has 3 terminals, the gate, the source, and the drain. Here we make the usual assumption that a 1 represents high voltage and a 0 represents low voltage. Notion of whether a path for the current to flow through is easily modeled by a switch. The switch consists of 2 fixed terminals corresponding to S and D terminals on the transistor. In addition, there is a movable contact. Depending on its position, determines whether the switch is open or closed. Since we're looking at logic behavior, this control voltage is represented on the symbol by the input variable X on the gate terminal. For an N-channel transistor, the contact is open for the input variable X equal to 0 and closed for the input variable X equal to 1. Such a contact is traditionally referred to as being normally open, that is, open without a positive voltage applied to activate or close it. Now let's look at the P-channel version. Here we see the P-channel transistor. The positions of the source and the drain are seen to be interchanged relative to their positions in the N-channel transistor. The voltage applied between the gate and the source determines whether a path exists between the drain and the source. Here a path exists when X is equal to 0 and it's broken when X is equal to 1. The transistor has a normally closed contact through which a path exists for X equal to 0. No path exists through for the contact X equal to 1. A circuit made up of switches that model transistors can be used for CMOS logic. The circuit implements the function f if there is a path through the circuit for f equal to 1 and no path through the circuit for f equal to 0. Here we see a simple circuit of a p-channel transistor switch model. The function G1 implemented by the circuit can be determined by finding the input combinations for which a path exists through the circuit. In order for the path to exist through G1, both switches must be closed, that is, the path exists for X0 and Y0 both equal to 1. This implies that X equals 0 and Y equals 0. So this is actually X nor Y. In this example, a path exists through the N-channel switch model circuit if either switch is closed, so this one actually implements X or Y. In general, switches in series give an AND function, while switches in parallel give an OR function. By using these circuit functions to produce paths in a circuit that attach logic 1 or logic 0 to an output, we can implement a logic function on the output. We can use these as the basis for more complex gates. The parameters that are important in the design space are fan-in, which specifies the number of inputs available on a gate. Fan-out specifies the number of standard loads driven by a gate output. Maximum fan-out for an output specifies the fan-out that the output can drive without impairing gate performance. And noise margin is the maximum external noise voltage superimposed on a normal input value that will not cause an undesirable change in circuit output. Cost for a gate specifies a measure of its contribution to the cost of the integrated circuit containing it. Usually this is based on the area used for layout. Propagation delay is the time required for a change in value of the signal to propagate from input to output. The operating speed of a circuit is inversely related to the longest propagation delays through the gates of the circuit. Finally, power consumption is the power drawn from the power supply and consumed by the gates. Thanks so much for watching. We're getting closer to the finish line every